Welcome to our exploration of exponential decay. In the natural world, many things don't change at a constant rate, instead, they change proportionally to their current size. Whether it is the cooling of a cup of coffee or the radioactive breakdown of atoms, understanding the calculus behind these processes allows us to predict the future state of a system with incredible precision. Why does this matter? Imagine a pharmacy calculating how long a medicine stays in a patient's bloodstream, or an archaeologist dating an ancient artifact. In all these cases, the amount of material remaining is constantly decreasing, and the speed of the decrease is tied directly to how much is left. This relationship is the heart of exponential decay. Recall your basic derivative rules. The derivative of an exponential function involves the chain rule, where the constant in the exponent is brought down as a multiplier. For decay, this constant will be negative, reflecting a downward slope. This mathematical property is the foundation of the differential equations we are about to solve. This is the primary equation for exponential decay. N0 represents our starting point at time 0. The variables t represents time, and decay is a positive constant that determines how fast the decay occurs. The negative sign is crucial. It ensures that as time increases, the value of the function decreases toward 0, but theoretically never reaches it. In calculus terms, we describe decay using a differential equation, dn dt equals negative k times n. This tells us that the rate of change of n with respect to time is directly proportional to the current value of n. If you have twice as much material, it decays twice as fast. This proportional relationship defines the exponential nature of the process. Look at the geometry of the curve. At the beginning, when n is large, the slope of the tangent line is very steep and negative. As n gets smaller and approaches the x-axis, the slope flattens out. This visualizes our differential equation perfectly. As the value on the y-axis drops, the speed of the drop slows down accordingly. The decay constant Ek is the speed limit of the process. A large k value means the substance disappears quickly, resulting in a very sharp drop-off. A small k value means the substance is more stable and lingers longer. Every specific material or scenario has its own unique k value that we must determine through observation or given data. Let's solve a problem. Suppose we have 100 grams of a substance with a decay constant of 0.05 per year. We want to find how much remains after 10 years. First, we identify our knowns. N0 is 100, K is 0.05, and T is 10. We plug these into our primary decay formula to begin the calculation. Next, we simplify the exponent. Negative 0.05 times 10 gives us negative 0.5. Using a calculator, we find that e raised to the power of negative 0.5 is approximately 0.6065. Multiplying this by our initial 100 grams gives us a final amount of 60.65 grams. We have lost nearly 40% of our material over the decade. What if we want to know how fast it is decaying at exactly that 10-year mark? We use our differential equation. We multiply our constant k, which is 0.05, by the current amount, 60.65. This gives us a rate of negative 3.03 grams per year. The negative sign confirms the amount is decreasing at that specific moment. Often, we need to work backward to find time. If we start with 100 grams, how long until only 20 grams remain? We set our equation to 20 equals 100 times e to the power of negative 0.05 t. To solve for t, we must isolate the exponential term and then use logarithms to unlock the exponent. Dividing both sides by 100 gives us 0.2. Taking the natural log of both sides allows us to bring the exponent down. The natural log of 0.2 is roughly negative 1.609. Dividing that by negative 0.05, we find that it takes approximately 32.2 years for the substance to decay down to 20 grams. A more advanced application is Newton's law of cooling. This is still exponential decay, but the value decays toward a floor, the surrounding temperature, rather than 0. The difference between the object's temperature and the room's temperature follows the exact same calculus rules we just discussed, showing the versatility of the model. On this graph, you see the temperature approaching the room temperature of 20 degrees. The rate of cooling is fastest when the coffee is hottest. As the temperature difference shrinks, the cooling slows down. The horizontal dashed line acts as an asymptote, a limit that the function approaches but never quite crosses. What happens in extreme cases? If the decay constant K is extremely large, the substance disappears almost instantly. In mathematical modeling, this looks like a vertical drop. This is used to model things like the discharge of a capacitor in a high-speed circuit or the decay of extremely unstable subatomic particles. Conversely, if K is very close to zero, the rate of change is so slow that the amount appears constant over human timescales. This is how we model stable isotopes or materials with half-lives spanning billions of years. The calculus remains the same, but the scale of time shifts from seconds to eons. One edge case to consider is when the data is discrete rather than continuous. While calculus assumes a smooth, unbroken curve, real-world data like population counts are whole numbers. However, when the numbers are large enough, the continuous exponential model provides an incredibly accurate approximation for these discrete steps. The most common mistake is forgetting the negative sign in the exponent. Without it, you are modeling exponential growth, like a population explosion or compound interest. Always check your results. If your decay problem results in a number larger than your starting amount, you likely missed that crucial negative sign. Another frequent error involves units. If your decay constant K is defined in per year, but your time t is given in months, your calculation will be wrong. You must always convert them to the same unit before plugging them into the formula. Consistency in units is just as important as the numbers themselves. When solving for time, ensure you use the natural logarithm, abbreviated as ELN, which has a base of Li. Using the common logarithm, or log base 10, is a common pitfall that will lead to an incorrect answer. Remember, ln and e are inverse functions that work together to simplify your equations. Let's summarize. We've learned that exponential decay occurs when the rate of loss is proportional to the current amount. This relationship is expressed by a simple differential equation whose solution is the exponential decay formula. We've seen how the constant K dictates the speed and how half-life provides a consistent measure of time. To solve any decay problem, identify your starting value, your decay constant, and your time. Use the exponential formula for direct calculations, and use natural logarithms if you need to work backward to find the time or the decay constant. This systematic approach will allow you to master any rate of change problem. To wrap up, try this: if a substance decays from 80 grams to 40 grams in 5 years, what is its decay constant K? Since it reached half its value, 5 years is the half-life. You can solve this by setting 0.5 equal to e to the negative 5k. Thank you for learning with us. Generated by Vision Solve AI.